Welcome everyone. Thank you for attending Programming with Effect Handlers and FBIP in Koka. I'm Dan Leijen. I work at Microsoft Research, and I do this together with Ningning Xie, who did her PhD at the University of Hong Kong. Um, so I think it's going to be very cool content this time. First, this is kind of our agenda. In the Q&A tab, I think it's best to ask questions because it shows up, and then Ning Ning or me can like promote you to speak and ask questions and interrupt me, and that's just fine. Or Ning Ning. We'll have 5-minute breaks between each slot, so there will be two 90-minute parts, each like chopped up in 25-minute parts. So the first time I will talk about a primer on Koka, like how the compiler is doing, the status, and give a bit of overview about syntax, and especially talk about effect typing and why this is important. And then in the second part, we really go into algebraic effect handlers, how they work, and what you can do with them. And then the third part, Ning Ning will give us like a deep dive in the operational semantics and evidence passing. I think that's very interesting. Then we have a 30-minute break. And then after that, I'll talk about functional but in-place algorithms. Exciting stuff. And then Ning Ning will again do like a more theoretical background of that with the linear resource calculus. And then after that, we're going to do advanced effect handler stuff, like linear effects or named handlers. And there's also be a lot of time to do like a live Q&A and tailor to your interests. So first, I wanted to say a bit like why we do the effect handler tutorial in FBIP in Koka, and that's because the current compiler and language support a lot of these novel items, and in particular in a typed way. So nice things about Koka is that it has a very small, strict core language, basically system F plus effect types and handlers. And in the end, it actually gets compiled down to just plain system F. And then everything else is kind of syntactic sugar. So we have a very clear foundational system on which you can reason very well. Moreover, every function has effect types, including things like exceptions and divergence. So it becomes very integrated whole, and I'll get to that later. And then, of course, there's typed algebraic effect handlers. So recently, effect handlers really took off, and Koka is one of the languages that supports that, like from day one in a strongly typed setting. So all the many things that are kind of baked into many languages, like side effecting computation or dynamic binding or rich control flow, like exceptions or async await, all of these are all expressed in terms of one abstraction, the algebraic effect handlers. So you can define all these things as a library in the language itself, and that's kind of part of the minimal but general philosophy of Koka. So we try to not bake in special things in the compiler itself. And then finally, recently, we did Perceus reference counting system, and it means we'll get to that in the second part. But it's really a compiler guided reference counting system, and it means there's no garbage collector or runtime system. It can generate C code that just links with libc, and that's it, right? You could link it with other things, and it makes it very portable, right? And this is also what allows the functional but in place algorithms that we're going to discuss in the second part. So I thought I'll first give a little demonstration, and if you want, you can even like follow along at home and install, for example, Koka with me and try out some examples that I'm going to do during the presentation. So if you go to kokalang.org, you'll end up in the page that looks like this. So here's a page, and it has like it has a nice documentation. Actually, a lot of things that I'm going to discuss today are described here as well, and it's quite easy nowadays to. Let me actually refresh it. Let's see if we get the live you can kind of install the compiler, hopefully easily. We did a lot of work on this, so you can basically copy this link, and then we can go to a development prompt. And if I just paste the link, you can kind of install Koka in an easy way. Now everybody knows my password, I guess. Oh no, it's still good. Yeah, and then it installs, and you can, in my case, have to remove previous versions. And then if you run Koka, you'll see it running. So right here we see, I hope everybody can read the prompt. Is the font big enough? Okay, great. Good to hear. So yeah, you can see Koka is running here. It's running. I took out my M1 this time, so we're on ARM64, and then you can type expressions in the prompt and run them, or you can, for example, ask what the type is of print. Let me see, of the identity function, or you can run small programs like let's write a hello world. Hello world. And we can also ask the type, of course, of that particular expression if we want. And we see here that print line has a console effect. So we get to all of this, and I'll give more examples soon. And if you want, yeah, you can try to install it yourself, and then you can go along with some of the exercises I'll do later on. For now, I'll exit here, and we can do other things. Let me see. Back to the. Yeah, over the last year, a lot of stuff has happened in Koka, in particular the new C backend, and we had many contributors. And I want to just do a shout out, say thank you everyone in the past year for helping out with lots of stuff. Yeah, much things have happened. Rashika did like improve the simplifier. Yu Kong worked on named handlers. Steven Fontanella did cross-module specialization of functions like map and stuff. The students Naoya and Kazuki did a lot of stuff on open floating and row type inference. Anton Lorenz, a master student who works on borrowing and improved reuse analysis. Alex Reinking did the first Perceus. Ningning Xie did lambda lifting, and tons of theoretical work that you'll talk about during this tutorial. At FWCD, added like Visual Studio, VS Code extensions and language servers. And there's many other people that have contributed, and many interns over the years have contributed to the code base. So thanks so much. Very soon there will be a new release with even more good stuff. So we'll see how that goes. It's not quite ready for production use, but I think it's very, very fun to work on it, like as a PhD student, or if you want to experiment with effects and FBIP programs. Lots of things to do, so please join if you feel like it. I thought one thing I wanted to show a bit, just to give an idea where the compiler is. There is some deep optimizations that are kind of hard, that they are implemented, and it's kind of cool to see how, for example, the map function is translated in Koka. And I'll just give a highlight. We'll get into many details later on. But we have, for example, tail recursion modulo cons, functional but in place updating, inlining, and evidence passing. So if you look at a function like cons, like here, a function like map, like here, you can see we write it naively. Map is not tail recursive, but because we do tail recursion modulo cons, actually we can make this into a tail call because all the rest around it is still pure. So the cons can be done like in advance, and then we can make a tail call to map. So if you actually look at the generated code, here's kind of the C code that's generated. We see the match on the list is like, are you a cons? And then you see the reference counting coming in. It says like, well, if you're unique, then we can try to reuse you, right? So that will happen. So first, f of x will be calculated, of the head. And then it says, I'll get to the if yielding. Then it in place updates that access.head with the new results because it knows it was unique. We can just reuse it as is. And then we do a direct tail call back to the while loop. We kind of update our accumulated result and keep going with the next node. So we're really going once through the list without using extra stack space, updating the list in place if it happens to be unique. And that's kind of special, I think. I've not seen any compiler that can do that right now. The other thing is...
we got one question. About modular counts. So that's from EBSCO. And he asks, modular counts is modular list counts or modular any constructors?
It's modulo any constructors. And even modulo like deeply nested constructors, like a node of something, right? With total functions around it. Yeah, it's very nice. It really helps writing very clear code where you're not worried about creating accumulating arguments. So this is quite powerful, right? Thanks for the question. Another cool thing I think is that you see it here, like there's there could effects be happening. That is the effect polymorphism right here, the E. So you do see that in the C code there will be like if we're yielding, which means like, well, if F, the function here we're calling, has some very special control operation, like say async await, that's defined using algebraic effect handlers, well, then you have to do special stuff. So usually we have like a happy path for unique things that are not yielding. And then there's unhappy paths where we're going to be slower, like to build continuations or to allocate fresh nodes. But this is how it's currently working. And this works out quite well. So I think I want to show a short example of that before we get into the real interesting stuff. I wanted to show here how you write a red-black tree rebalancing map in Koka, like Okazaki style red-black tree rebalancing versus the C++ in-place mutating red-black tree, which is standard map. It is very optimized implementation of red-black trees. So again, if I go here and remove the news, then here's a red-black tree in Koka. So we have like some data types for the colors or for tree nodes that have a color. And then we can do left balancing. You see there's many matches going on, or right balancing. And then finally insertion. And this is basically a copy of Okazaki's red-black tree implementation in the book. And you see it's purely functional. It gets a tree and returns a new tree that's better, right? So if we, let's say we're going to compile this in Koka. Actually, I'm going to go to my own amazing... I'm going to use the Koka development version. So we can do compilation and we do optimization. And then we're going to do a test bench. Koka red-black tree. I'm going to... so now it's compiled, and we've compiled into here a Clang debug release version, and I can now time it, right? So I can like run that, and it will do 42 million insertions in the tree that are all rebalancing in a purely functional way. Let me do one more time because because I'm presenting, I don't get the normal numbers, but 0.5 seconds. It's usually a tad faster. So let's compare that to C++ with the standard.map, which uses its own red-black tree under the hood that is highly optimized. But it's a big difference. It's like an in-place mutating algorithm. It looks terrible, right, compared to the beautiful pure function. But let's see how much faster it is. So we can C++ 17. Let's call it CPP RB3. And of course, we're going to optimize crazy. And then test, bench, C++, red-black tree. There we go. And then we can time that program, CPP RB3. 0.45 seconds. Oh my God. This is so this is very close. to the naive Koka compiler, which is kind of amazing because we're comparing to the in-place updating one. Well, we actually wrote a persistent functional insertion, right, of the same number of nodes. So this is very encouraging. No garbage collection, no other runtime system. We can compare also like to GHC. Let me see, O2, I guess. RB3. So I wrote the same one with strictness annotation and made it as fast as I can make it. HS, right? That will do the trick. Wow, it's so fast. Okay. Time, HS. 1.3 seconds. Still very good. Amazing, right? The Haskell compiler. But you can kind of see that if you start with a language that has like strictness built in, it's easier to compile that, right? So I think there's a lot of opportunity here to do much more, but it's very encouraging, right? All right. Let me see what the timing is. Okay, good. So I thought let's give a little overview of the syntax of Koka before we dive into effect handlers, especially with syntax. It is very important here. We already saw a little Hello World program, so that's kind of obvious, but there's already something to be learned there. I kind of chose to do brace syntax to be more close to many other languages.
We just got one more question. I think it's regarding the performance of GHC. So Alex asks, is that the performance of GHC because of loss of GC overhead?
Yes, that's a good question, right? So why is it slower, right? And I think we it's hard to say. Like we tried to many other languages too, like Swift and stuff. And the GC, in a way, Haskell can allocate really quick as a bump allocator, right? But until it needs to garbage collect. But on the other hand, this benchmark has lots of like cheap garbage, so not sure. But I think it is the garbage collection overhead mostly. Yes. Because the Haskell will all the time allocate new nodes when it's rebalancing. So yes, it's like cheap garbage, can be collected quickly, but it does allocate all the time, every time it has to rebalance the spine. While with the reference counting implementation in this benchmark, Koka will like update the rebalance spine in place. And we'll get to that in the second part of the talk. I'll explain how that works. And I think that's where it comes from, right? But they're all big systems. In the end, there's lots of things, right, that could play a role, right? It's for the Haskell one, it's not laziness because we carefully wrote it to be as strict as we can, right? So
we got a follow-up question from Gwenlomi. Sorry for mangling names. And he says, I guess an interesting comparison with ML with GC with the source code as similar as possible.
So, yeah, I don't want to run ahead to the next part of the talk, but later we're going to do FBIP algorithms, and then I'm going to show actually benchmarks also against the Camel. So Camel is much closer. It's like 1.25 times slower than Koka on that same benchmark, while Haskell is like 2.5 times, right? So there it's much closer. Although on other benchmarks, you see again that the garbage collector has an influence, right? Yeah. So, but OCaml is also it has a very good optimizer, and Koka is not even close to that right now. So, I think it is garbage collection is a big factor here. It's still early days, right? So we don't know. I'm sure we can come up with workloads where we don't do so great, right? I show you the nice one, but don't tell anyone, right? But we'll get so in the later part in the talk, we'll look actually at more benchmarks and see that it is all described in a PLDI paper just a few months ago called Perceus Garbage-Free Reference Count Unit Reuse. Anyway, one thing you can see in the hello world is we use parentheses for function calls, just like math, I like to say. And it's good for error messages as well. But the real reason is that we want to be very specific about when effects can happen and when not. And if you have queried application like fxy, you kind of don't know if there would be effects between the application of fx or a later application to y. And in Koka, this kind of becomes more explicit because you either have one function call with xy, or you have f applied to x and then the function is returned, and now you apply y. So it's kind of for effectful languages, it's kind of important to have basically multi-argument application to make that explicit. Another thing that we use a lot in Koka is the dot syntax. So instead of writing it all like this, where you print the length of a map over a list of increments, we write it often more like this. We like a list from 1 to 3, and we map increment over it, and then we take the length, and then we print the length. And this is very convenient, right? And this is basically just syntactical sugar for putting the expression before the dot as a first argument. But yeah, it's surprisingly useful. Use it all the time. Let me see. Trailing lambdas, right? So another thing of being minimal but most general is that we want to use functions all the time to do control flow constructs. So like here is a for 1 to 10, and then I have an anonymous function here that prints where you are in the loop. And this happens a lot, of course. Haskell programmers or Camel programmers, right? We do this all the time. But it's kind of cumbersome with long function bodies. So a contrast to the parentheses, we can have trailing lambdas. So you can actually put them behind the parentheses, but it's actually equivalent to giving it as a last argument. So now you can kind of have this for loop with its body, right, as a regular lambda expression. And this happens a lot in many cases. Like there's also, for example, let me see here, the repeat one. So the nice thing is that if a function has no arguments, like here, we can also write it with just the braces, which you could kind of see as suspenders, right? And I think when you look here, you can say, oh, do 10 times this loop. And now it really looks like just your regular C function body. But it's really just an anonymous lambda, and it expanded to repeat 10 with an anonymous lambda. So the core is still very small, but we use this syntactic sugar to make the code just much nicer to work with. And these little things matter a lot in larger code bases. You can really notice that. An interesting thing here is with the while. So normally languages, the while condition is between parentheses. But while is just a function in Koka. It takes two functions as arguments, namely the predicate and the body. And you can see that the predicate now is in braces as an anonymous function. And that makes a lot of sense because the predicate will be evaluated once or multiple times, right? It's not like a value that's evaluated once. And I kind of argue that in C and Java and I don't know, almost all languages, that's kind of a mistake to have parentheses there because it's really different than function calls, where between parentheses you always evaluate before the call. So while with braces, although we don't often use while, of course. Ooh, I already getting to the 25-minute mark. I will take a few more minutes here because I think with syntax is really important for the rest of the talk. So let's discuss that. So often you have nested lambdas. You have a function twice that takes a function as an argument that executes it twice. So you could write it like this in Koka, where I give two anonymous lambda expressions to twice. But we have with syntax that makes it nicer to write, where you don't get the indentation. So you can say with twice, and then everything under it becomes automatically wrapped inside these braces as if it's an anonymous function that you pass in. And then I can do again like with twice, and then everything under it again is passed there as its body. And this is used a lot with algebraic effect handler. So you will write a handler takes always an action and lambda as its argument. So we can actually write with handler blah blah blah, and then everything under it will be scoped under that handler. But again, it's just light syntactic sugar for doing lambda calculus in a good way. Yeah, so with is used a lot, and make sure that when you see with statements, you really read it as like everything else under it is kind of scoped under it, and can be executed once or never or many times or in a special way, like if you have effect handlers. And one nice thing that happens here when you deal with resources is you can write finally is a regular function. So you can write with finally, and the first argument of finally is what to do when you return from this scope. Well, in this case, you will print exiting. And then the next argument is like an anonymous lambda for what you want to do, the action. And in this case, because we use with, it's like scoped all under it, right? So this is all just syntactic sugar for an explicit call to finally. But this is very convenient, right? And now we don't have anything built in. Like in Go, for example, you have the defer statement that does the same thing. We don't need that in Koka. It's all with syntax and algebraic effects. I'm going to skip this. I think, we need to talk about effect types, but I think we want to take a short break, I think. And then we'll be back in 2 minutes, and then I will start here, I guess. So this is in a way orthogonal to algebraic effect handlers. It's about how can you keep track of effects in the typing. And it turns out that in Koka, we use row-type polymorphism, and that works really well with algebraic effect handlers. So the idea is that every function, like here square, has like not just input and output type, but also a effect type. In this case, like we say, well, square is total. It will not raise an exception and never diverge. But a function like error, well, maybe it has an exception effect. Or Turing machines have a divergence effect. Or if you print, you'll have a console effect, as we saw earlier. And sometimes things are even polymorphic, like map has no effect on its own, but the effect it has depends on the function you're applying to every element in that list. And I think these effect types are really important to kind of reason about the semantics. Like it's really nice if you're in a total fragment, and you cannot fake this in Koka, right? It's very strict about it. So the compiler can reason about it. And what it really means is that these effect types gives you a way to say, what would be the mathematical function that models my program, like the denotational semantics? What would its type be if I want to write that, right? So for total functions, it's kind of obvious this is how we usually think about things. Like an int to int is really natural numbers to natural numbers. But if you have an exception type, well, then to model such computations, you need a richer result type. You're like either a result or an exception, like a constant in the category. And this is detectable. You can like say later, I can handle it. I can either do something on the exceptional result or the real result. And then we have an effect, we call it pure, which is exceptions and possible divergence. So that's always harder to model denotationally, but divergence is usually done by injecting a bottom element, which says like, well, if you kind of don't know, right? So like inject it into the set. And this is different than the plus because it's not, you can't detect it. You can't like match on bottom or something. And in many languages, like say C or something, they're more in an effect like this, where there's like some arbitrary heap and exceptions and divergence. So you really have some heap that comes in and a heap that comes out, right? And you may diverge and there may be exceptions. And now it's very difficult to really reason about your programs. So nice in Koka, I think maybe 80% of your functions will be total, like surprisingly many, right? And then there's like 15% that may also raise exceptions or diverge. And then there's a little bit left over that's actually here, right? Where you interact with the real world. So that's very similar, I think, to the experience with Haskell with the IO monad. Let me see. So we use row types to denote those types. So total is like there's no effect at all. While, for example, pure will be a row with exception and divergence in it, right? And we call that pure because that is very close to how it corresponds to Haskell's notion of purity, right? Where any value can be maybe diverge or raise an exception, right? I think a big thing, because Koka is strict, right? Only functions can have effects. Only when you do something, there is an effect. So the effects are always on the arrows, but never on the values. While in a lazy language, every value itself is like bottom injected, so it could still raise or diverge. So let me say, of course, you need the row type polymorphism. So we always talk about like closed rows where there's no end, it just ends, or open rows, and they can have like more effects still. So you say you have some effects and maybe more, and that's the polymorphism. And we already saw that in the map example where the final effect is determined by the function you're passing in. Another interesting aspect, I think, to show here is that you can have duplicate labels. So you could have types like exception effect, divergence. It's a bit like having a monad transformer with multiple exception transformers in there. And sometimes you can't swap those. And sometimes it matters, like with the state that's parameterized over a heap, we can't say that that's equal to this row, right? We can't swap them around. And these duplicates occur naturally during type inference. So it's kind of important to think about that. So here, for example, with the catch, you see that an action can have an exception effect, but I also give a handler that will handle any exception. So the final effect does not include exceptions, right? It's just all the other effects that are still there. But now you can imagine that handle itself will raise an exception. And in that case, like that E will unify with exception, and that will mean that this type here will be exception, right? And this is important, like, and so during type inference, this occurs, naturally, right? And it really shows that there's like two exception handlers in the context. All right, great. So now we actually get to the second part.
Before we move to the second part, we got one interesting question. So Alice asks if you have something like where you have a tuple and that you apply an effect for function twice, how are effects sequenced?
I need to read. Sorry. I need to read it. Fx, Fy. Yes. So the Koka has a strict left to right ordering in argument evaluation. So this is it's strictly defined that all arguments are evaluated from left to right, top to bottom through the statements. So that it doesn't. Right. So then Etzko asks, well, even if it's all total, so then there would be a compiler optimization, right? So if the compiler detects that the functions you apply are total, or that the effects you're using are commutative, then it could maybe optimize that to be different, right? But otherwise, it must really be very strict about such things, because non-determinism is like a separate effect. So the idea is that if you have a Koka program without funny side effects, now actually with side effects, right, you will get deterministic answers as long as the ended effect is not there, right? And this is sometimes actually very hard to do because with double arithmetic, I keep having trouble across platforms where the results slightly different. Right. Okay. So let's continue with algebraic effects because that's really what we're all here for. Right, but maybe right to the question was very good. I think with Koka, it's all about deterministic outcomes, unless there's the ended effect in your effect type, and now you're more like in an IO monad, like in Haskell. But we try to avoid that, of course, as long as we can. Basic effect handlers. So algebraic effect handlers are fairly new. Like in 2009, Mattia Pretnar and Gordon Plotkin published their first handling paper where they define like a categorical semantics, and it turned out it would work really well with Koka, and so we all implemented that. And here's an example of an effect handler in Koka. So suppose we want to define how exceptions work, and this is actually how exceptions are defined in Koka, right? So here we define first a new effect type called exception, and then you define a bunch of operations that belong to that, right? The non-proper morphisms of the monad, so to say. So here I define a control operation that's like the most general form. We'll later see there's others like fun and val. And we can say, well, we can throw with some message, and since we know that throw will never return, we can give it any result type, right? So it's for all alpha, which is very funny. Only exceptions really have that. And then when you define this, you can already program against the interface. You can use throw because we know its type. So you can write a safe divide that divides x and y, and it will say, well, if y is 0, then I call throw, and since it's for all alpha, it can unify with int. So now we get a function that get the exception type because we're using throw, and returns an integer. And now we can give different implementations of what exceptions mean through handlers. So the handlers give the semantics to the effect. And that's what's happening here. So here I make I use my with syntax. Here's the expansion of that to define a handler that says, well, if someone calls throw in the action under here, right? That's the argument to the handler because we use the with statement here. Then you go all the way up to throw, and then you're just gonna replace yourself with 42 as the final result, and you just discard all the rest. So if you would like evaluate that, we will get something like a handler of action will be installed. We will remember that we have to do 8 plus, and then we go into save divide, and then eventually we're gonna call throw divide by 0 inside the save divide. And then we'll just go up all the way to the handler, like here, and then be replaced by its body. In this case, it's 42. And that's the answer, right? So it will just exactly how we expect handlers to work. The innermost handler catches the exception, and in this case, handles it by returning 42 to the context. And we can do more, right? Like other interesting handlers. So one interesting one is to reify effects back to the value world. So in this case, you can make a handler that reifies it back to a maybe type. So here we use with again. We leave out the handler keyword here, and that's kind of just shorthand. So if there's just one operation, you can leave out handler. And this happens a lot, so we will see this a lot. So I just say, with the control operator throw, if someone throws in action, I'll just return nothing. But if the action succeeds normally with the result, I'll wrap just around it, right? So now we reify back to maybe types. And you can call to maybe with save divide 1 0, and here the action, it's like the anonymous lambda again that we pass in. And you can see in the typing now that we used to have here exception E, but we handle the exception in the action. So we only have E as the final result of 2 maybe. But now we have a maybe type, right? So we switch from the effects to the value world. And we can also go back, of course. And I think there's lots of discussions online, especially Hacker News, right? Should we do value-based errors like try, or like in Swift try, or in C, or should you use exceptions like in C++? And what is better? But I feel like a false choice because you can reify between them. They're not essentially different, and whether you use one or the other really depends on your usage pattern. Like if you want to abstract from it, well, you use effects, so you don't have to mess up your beautiful control flow. But if you really want to deal with how you compose the different exceptions and stuff, maybe you want to reify it first to a value and reason about it that way. So we leave out handler. Right. So here's a generic catch handler. We just make it, instead of nothing and just, we can also have just a handler, right? That handles it in a particular way. Another, maybe the biggest thing with effect handlers, what is the difference now, right? With exceptions? Well, effect handlers can resume, right? So you can go back to the call site where the original operation was called. So one of the most basic forms of that is a reader effect. So we can define an effect ask of some particular type, and we define again a control operation ask, and it will return that particular type. So now it's not a polymorphic value, but it's determined by the effect type. So I can already use it. So I can do add twice, and it says, well, give me a context where I can ask for integers. So you ask an int here, you ask another int, and then you add them up together to get the final result. And then we can define handlers for it. So here's a very simple handler. It says, well, with the control operator ask, when you're called, you just resume to your call site with the result 21. So with exceptions, we would like directly just return a value like 42 and be done, like a stop to computation. In this case, we're actually going to go back to our original call site and return with the result. So this is really like a dynamically bound function in your scope that you can use. And then when add twice is called, it will twice go there. I think I have an animation on that. There we go. So here we see the handler for ask is installed. And then we still have to do the plus ask here. But we are with the first ask. So it will go up all the way to the handler and replace with the body. That's resume 21. But it will also capture the entire original context, including the handler. So we call this deep resumptions because the handler is part of the thing that's captured. And when we call resume, we restore the whole thing again, but we're going to put 21 in the final result. So when we resume, it all comes back, and we result in a final result of 21. And then, of course, the same happens with the second ask. So there will be 21. And then we just return through it, and we'll get 42 again as a final result. And this is very powerful, that we can kind of have resumable exceptions, and it's a valid way to look at effect handlers. And here, what you also see is that effect handling can be expensive because we had to capture that entire context, including the handler. Right? Here's another handler, just to show something else. So in the previous one, we see that we became total because we handled all ask effects, and there was nothing else, no other effects. Here I have a random ask. Here I say I resume with random integers. But to get random integers, I have the random effect. Like somewhere out further, someone needs to define what the random number generator is with another handler. So this is a common occurrence where you transform from one effect to the other, right? For example, with mocking, like you don't want to use print line, you want to use log, but maybe a different implementations of how you want to log. So just depending on the handler you're going to give, you can use logging. Right. So here's an example. We used control all the time here. in the sense of control operations that maybe do something with your control flow, like exceptions did. But in this case, it's almost like calling a function, right? We just resume with a particular result. It's like going back to your call site with the result. The only difference with regular functions is that it's dynamically bound in your scope, statically typed, but dynamically bound. So we make this easier because this happens actually a lot. Like I would say 90% of all the handlers you're ever going to define will be of this form, where resume is the tail call of your operation and you don't use it anywhere else. So in those cases, you can just write fun instead of control, and it signifies something to the compiler that it will have this particular form, and they can be implemented much more efficiently. In particular, you don't have to capture the whole resumption, but you can execute them in place, and Ning will later show how that works. So actually, we can write this function as with function ask just random int. That's the result. Like, and implicitly there's a resume here. And now it's no longer in a sense a control operation, right? It's just saying like we have some function that we dynamically bind, and they can be, it depends in the context how these operations behave, but it will not mess with your control flow. There will be like not like exceptions or async await. There will be just returning values. So here's a nice example of that. I think that is like common, like in many languages. You want to like emit something or log something. So you want to say have an effect that emits. So actually, it's again like a nice shorthand. I don't know where. There we go. If you just say effect and then immediately give an operation, it's like implicitly defines a type of the same name as the operation, and then you can use that. So here I can already say, okay, with function emit, I'm just going to print it, right? So now we transform an emit effect into a console effect. I should actually use my pen a bit more. My emit into a console, and of course you can have many other effects, but we keep those around, right? So we just changed emit to console. This is not right. This is right. It's like an effect transformer, right? And that works out really well. And this is, I think, often how effects are used. For example, maybe you have a substitution in your environment, or maybe you actually have an actual writer monad where you just output stuff. And a cool thing that Koka has are local variables. We'll get to that in a second. And those actually are shorthands for built-in state handlers, as you will see later. But it's really convenient because, for example, I can make a handler here for emitting that will like just collect all the lines in some list. And I'm like locally updating the state here. It starts at empty list, and then I keep consing on it until I'm done. And then there's a special return handler that says, well, when you're done with some result X, we're going to discard that result, but we take the current lines, we reverse them, and we join them. We do something with it, and then return that, right? And I think the interesting part is that this handler can kind of have local state here. So it's very kind of organized, structured, just contained here. But the action doesn't know about this state, nor does the emit collect show that it's using like local mutation internally. It's like unobservable mutation. It's very natural to use this, but you still get like pure functions out of it. The action doesn't know there's local mutation going on. It just knows it can emit, and then the final result is just a string, and the emit effect is handled. And I think this is a very powerful thing. It allows you, through the handlers, to kind of define a little interface that says, these are my interface. You can like say substitute variables. And internally, you can just encapsulate statefulness there as in a regular function, not in an object or a heap where it's like where it would globally leak. And then only access that state like in a very structured way, right? Only through in this case, the emit interface. So this I think is where a lot of power of effect handlers comes in. Think about unique name generation or something, right? That these are always troublesome, or for the reader, like options, right? Like global options that you want to pass along. Yeah. So Etzko asked, I don't understand this example. Lines is a reference cell. Yes. So it wasn't clear. So this var says mutable variable, like usually use val in Koka for let bindings, and var for mutable bindings. And that's why I also write here like equals, like as an assignment. And later in the advanced section, we'll get to this, that actually this var is syntactic sugar for effect handlers. So the semantics are all defined as like a local stateful effect handler here. It's like a built-in effect handler for mutable state. And yes, it's like I just said, right? It is referentially transparent because, as we'll see later, it's not like this can escape its scope, because we don't get a handle on the actual reference cell. We just get a secret handler in scope that deals with that has like a get and set operations, right? But they're not exposed anywhere in the type. But we'll see that later in the advanced section. I think it's too much now to go through it. I want to show some other examples first. Let me see. Yeah, it's almost time for the break. I wanted to show like I'll take 2 more minutes to show some other cool things that effect handlers can do. I think this is cool work I did with Jonathan Brachthauser during his internship. So we had this. It's a general question, right? Like often you have like global values that you want to think about. For example, in a pretty printer, you may have some particular width you want to restrict your output to, right? And it may be deep inside the pretty printer, like all kinds of function calls. So how do you deal with that, right? Like you either gonna add like an extra parameter everywhere and plumb around your max width, or you change everything to be monadic and then do the plumbing in the monad, but now you have to change all your code to kind of be monadic, etc. So here's where effects can be very useful, right? So in particular, we saw already the functions effect. Well, we also define value effects, and they're kind of functions that just return constants. So you can actually you can say, oh, I'm going to use width, and you just use the width in your internal function. And then at some point, you're going to use your pretty printing function. You just bind a handler there that says, okay, the width is 40. And again, it's just syntactic sugar for width function, width that always returns 40. But since it's a constant, again, the compiler can do like more efficient implementations. And I think it expresses the meaning better for what you want. There's actually a tech report about this that's maybe fun to read. Hopefully we'll publish it soon somewhere. I had one more, I think, cool thing I want to show that's not always understood well, is that handlers not only can capture evaluation context that you can resume later, but it can also change the context above themselves. So here's an example of that, of a funny control operator. It's called tick, and it resumes with like a unit result, but it leaves like a little piece on the stack called 1+, right? So it's not a tail resumptive handler, so we can't use fun there. And it has the following behavior. So if you're here, we have like a handler for ticks, and then there's still stuff to do, and we get to the first tick. Well, the resume will again like capture the whole thing, the context, until the point where we were. But there will be this 1+ here on the stack, and when we resume, that is still there, just above the handler. So now we've changed the context just above the handler. And then with the second tick, the same happens, right? And now there's like 2 1+s above it. And then eventually we percolate the 1 up, and then in the end we'll get 3. But it also shows these are very risky kind of handlers where you're not tail resumptive, because now the depth of the stack will be the number of operations that I'm going to call. So this is dangerous stuff. But sometimes used, especially with multiple resumptions. But I think in practice, you have to be very careful with such kind of handlers, right? Well, again, I kind of misjudged the timing a bit. I see we're already almost at the 10:30 mark. So maybe let's take a mini break. Let me see how much I still have. Maybe Ning Ning, I'll continue and we'll start your session like a few minutes later, because this is just about the get and set composition.
Right, that's totally fine. Just feel free to finish the session first, I think.
Okay, I'll do a little bit more. Otherwise, it won't fit well after you do the theory section. Right?
Yeah.
Okay, so I wanted to show one more thing, like why are people so happy about effect handlers? Well, one thing is that they compose freely because they're basically like free monads. And here's like an example of that. So here's a simple state handler. So you can get and set, and again, I use this mutable variable here. So get just returns the current value, and set will update it. So again, I use like local state to implement it, a state handler here. And as you can see, it will do the action, but then left to right evaluation gets the final state as well. So it will return the result and the final state is an integer. And I think here we're gonna do a test that uses both exceptions and state. So it sets something in the state, an increment, and then it actually, this should be throw, but then it throws ouch. And eventually it returns true, but it'll never get there. And then in contrast to, say, Haskell with monads, this doesn't determine yet like how they are composed. That really depends on how I compose the handlers. And there's two ways, right? I can do state on the outside and the maybe on the inside, or maybe on the outside and state on the inside. And this is really the combination of the two. And if you look at the types, they're different. So one of them says with the maybes on the inside, you will first get a maybe of bool, because I might raise an exception or not. And then the final state at the time the exception happened, right? So that's kind of usual when you have heaps and exceptions in most languages. But if I turn them around, I get the other way around. I either am successful with a Boolean in the final state, or I get nothing. And that's kind of like a transactional state, because I never see the state as it was when the exception happened, right? And I think, yeah, this is really cool. You can just freely combine handlers in any order and give, but you also get different semantics. So on the one hand, it's great. We get free composition of handlers. On the other hand, you still have to be very careful how you compose your handlers. And I think this is one reason why I think effect typing is really important, because it keeps your effects in check, right? You can always see like, oh, I haven't handled this effect yet, or I have a bunch of effects. How should I be handling them, right? Hey, and that's it, I think. Let's take a 3-minute break, and then Ning Ning will show us more of the theory behind the effect handlers, which will be very cool to see, I think, including evidence passing.
Yeah, so in this part, we focus more on the theoretical part of effect handlers. So let's start with a bit of history on algebraic effects. So algebraic effects were introduced by Plotkin and Power in 2003, and then algebraic effect handlers were introduced by Plotkin and Pretiner in 2009. And in this work, they established the theoretical semantics of algebraic effects and handlers. And since then, algebraic effects has been intensively studied. And for example, in this year's ICFP, you will be able to find like 4 or 5 papers about the algebraic effects. So as have been demonstrated by Dan, algebraic effects together with handlers provide a powerful and flexible way to add structured control flow abstraction to programming languages. And the nice thing I really like about the algebraic effects is that we can express various concepts, including states, exceptions, asynchronous I/O, within a single framework. So in this tutorial, we focus on algebraic effects in Koka. So I'm going to give some history stories on Koka. So Dan started Koka in his very initial paper about programming with row polymorphic effect types in MSFP 2014. And that work showed that effects can be treated in a disciplined way using row polymorphism. So we can see the effect a program may perform in its type signature, and we can get some static guarantees. For example, if a program does not declare that it has effect ask, then it won't perform ask. And at that point, the community is also actively investigating how algebraic effects can be implemented more efficiently. So later, the paper at Popo 2017 show how we can compile effect handlers with type-directed selective CPS translation to JavaScript. In particular, to be able to elaborate algebraic effects, we applied CPS continuation passing style, but a full CPS turns out to slow down the code significantly, and it has been long recognized that one can selectively CPS transform only parts of the program that need it. So in our case, we only have to use CPS translation on those parts that may issue effectful operations. And we can tell which part in the program may raise effectful operations from the effect type signature. So we get a type-directed CPS translation. But we are not very satisfied with JavaScript. And at the same time, one of the explosions is to do algebraic effects directly in C. But that's quite complicated and requires some magical primitives that capture the code stack. So we started to wonder if there is any way we can implement algebraic effects more straightforwardly, easier to maintain, and easier to reason. And so we get into the evidence passing of effect handlers, where we show that using evidence passing, we can go from algebraic effects into polymorphic lambda calculus and also have the idea implemented as a Haskell library. With the idea of evidence passing, we implemented a C backend for Koka. And at this year's ICFP, we improved upon our previous work. We will come back to the detailed comparison between these two ICFP works later, but most importantly, we are now able to compile full algebraic effects into standard C code efficiently. And together with our work on Perceus, we are able to get amazing performance results from Koka without needing any special runtime system. And there are still lots of undergoing works in further strengthening Koka, including the talk we gave this year at Hope to support first-class handler names and lots of implementation works. And with all the efforts, we ended up with today's Koka. But there are still plenty of rooms for further improvements. And so if you are interested, please come and join us in this Koka family tree. Yeah, so now enough with the history, and then in the rest of the talk, we will start touching the more theoretical aspect of algebraic effects, and we started by talking about the operational semantics of algebraic effects and the problem with compilation, and we discussed in more detail what evidence passing is. To be able to talk about the operational semantics, we first needed to know what syntax we are using. So these slides give the syntax of untapped algebraic effects, and where an expression is either a value or an application or a handle, and then a value is either a variable, a function, or effect handler, and an operation performed. So handle is only generated during evaluation by handler. So we treat handle as a strictly internal frame, and we will see how it is generated during evaluation later. And if we compare this syntax with untapped lambda calculus, we can see that we have only added the language constructs for handle and for perform. So this is like a minimal lambda calculus for algebraic effects. During evaluation, we also use the concept of an evaluation context. So an evaluation context is useful to indicate the evaluation order, and it is essentially an expression with a hole in it. And in code by value untapped lambda calculus, for example, an evaluation context is either an empty box, which we can plug expressions into, representing expressions that we are currently evaluating, or we are still working on the function part of an application, or after the function evaluates to a value, we can evaluate the argument. Then with algebraic effects, we get one more case where we can have a handle in the evaluation context, and we will show how it works in the operational semantics. So this is the syntax we will be using for our algebraic effects. And then now we turn to the operational semantics of untyped algebraic effects. And we will go through these operational semantics rules one by one. There are not many of these, it's just 4 rules, so please don't get scared. So the first rule is just the standard code by value beta reduction as in untyped lambda calculus. And then this handler rule is where we define a handler. And this computation f to be handled is always a unit taking function, which essentially corresponds to a suspended computation. And we execute this computation and turn a handler into a handle. And when handling a computation, there are 2 possible situations. In the first case, the computation evaluates to a value, so we remove handle and propagate the value. And in the second case, the computation performs an operation which is handled by a handler. And we have several things to note here. So first, this capital E is the evaluation context we have just described. And the evaluation context essentially represents a code stack. So that means we can perform an operation deep inside the code stack. But then how do we know which handler is used to handle this operation? Well, we will need to search through the code stack, find the innermost handler that will handle this operation, and get the operation implementation F from it. Now we are ready to apply F to the operation argument V as well as the resumption, which captures the whole evaluation context between handle and the operation code. So the operational semantics of algebraic effects is quite intuitive, but it becomes problematic when we want to compare algebraic effects efficiently. So the main problematic rule is perform, which includes 2 potentially expensive runtime operations. So first, since the perform can be deeply inside the evaluation context, we require H, and we require H to be the innermost handler. So that means we will need to perform a linear search through the current evaluation context. And second, after we find this handler clause F, we will need to provide the resumption. And that means we will need to capture the evaluation context up to the find handler and create a resumption function. So this is not only expensive, but might be impossible for some platforms like .NET or Wasm, where you have no access to stacks. So to see the problem more clearly, let's take an example. Suppose we have 3 handlers, ask, tick, and exception, and in the end, we just perform ask twice. Now let's take a closer look at how this expression evaluates. So we first evaluate the read handler. I called read, but I think Dan also calls the ask effect. And now we need to store this handler in the evaluation context, since later we may need to use this handler to handle certain operations. And then in a similar way, we will evaluate the tick handler and then the exception handler. And now we hit the first ask. But we don't know yet how to evaluate it. Thus, we yield up to the evaluation context and hope to find a handler for it. So the innermost handler is an exception handler, which is not useful in this case. So we keep going up, and we find a tick handler, which is again not useful in this case. And finally, we reach the read handler, which says that we should resume with integer 1. Okay, now we need to resume and go back to where the operation is handled. And this is where we hit the second ask. And now we need to repeat this whole process again by first yielding up and then resuming. So as we can see from this example, implementing algebraic effects this way is very inefficient. And it also often requires special runtime support to yield up, to capture the resumption, and to resume. So Koka deals with this problem using evidence passing. So what exactly is evidence passing? So in the left, we summarized what we would do to implement algebraic effects in traditional implementations where, as we have seen, we evaluate the program top-down, and when we hit the perform, we need to yield up to the handler stack and find the right handler and come back to resume. And this is inefficient and also requires special runtime support. Then the key idea of evidence passing is that a vector of handlers is passed down as an implicit parameter to all operation invocations as we evaluate this expression top-down. So we will be able to run some operations in place, and for example, in this case, we can run ask in place. And with this key idea from evidence passing, we can also elaborate from algebraic effects into polymorphic lambda calculus. So we can implement algebraic effects in a standard backend. Koka supports evidence passing since ICFP 2020. With evidence passing, we improved upon the existing JavaScript backend of Koka. So the original runtime part is about 1,000 lines of JavaScript, and the new implementation based on evidence passing requires just a few primitives. And we implemented an efficiency backend for Koka. And in this year, we published another paper that further improved upon the previous work. So here, we would like to give a clear comparison between these two works. So first of all, we call the techniques in ICFP 2020 evidence passing translation, and then in ICFP 2021, evidence passing semantics. So they share similar purpose, although EPT differs significantly from EPS. So the first difference is that, as the technical names have already implied, EPT maintains evidence vector during translation to an evidence calculus, and while EPS dynamically maintains evidence vector through direct operational semantics. And while EPS works for general algebraic effects, EPT only works for a subset of algebraic effects, restricted to what we call scoped resumptions, where a resumption can only be evaluated in the same evaluation context as it is captured under. And in the rest of the talk, we will explain in more detail how EPS works. And where audience who have attended our ICFP talk might have already been familiar with this part. So using evidence passing semantics, we give a formalized evaluation semantics from algebraic effects into a polymorphic lambda calculus, and show how this technique can be used to generate efficient C code with no special runtime support. And we achieve our goal using a sequence of refinements to the semantics of algebraic effects through multi-prompt delimited control, evidence passing semantics, leveling yields, and monadic translation. And we prove every transition is semantics preserving. And along the way, we also explore various interesting points in the design space. To demonstrate each transformation, we start with an example. We start by looking at the reader example, where we use the handler h1 to handle two operations, to perform ask. And the definition of h1 is given on the top right, and here the handler just says we are going to resume with the integer 1. So here the syntax is slightly different from the Koka examples, because here we are using the more formal semantics we defined for the untapped algebraic effects calculus, not strictly syntax in Koka. So we evaluate this program using the operational semantics we have just seen. So first, according to handler, we are going to execute the computation. And by app, we just substitute the unit away and get a handle expression. Now we evaluated the first perform, and we need to find the innermost handler, in this case h1. So we evaluate this expression into f, applied to the argument unit and the resumption. F says it's going to apply its second argument to 1, so its definition is given on the top right, and which further gives us this. And as the second perform ask will be handled in a similar manner, the final result would be 1 plus 1, which is 2. Now we can start our transformation. So the first transformation we apply is the multi-prompt semantics. And we first omit some less interesting details. With multi-prompt semantics, each handle is replaced by a prompt. And importantly, each prompt is associated with a fresh unique marker, in this case M1. Now when we do perform, we can search through the context and evaluate perform to yield M1, as we know exactly which handler to yield to. And we can also apply the operational implementation to the argument, as it now only waits for the resumption K. Now, prompt will handle yield, where we will capture the resumption and evaluate to the same expression as before, except now we have replaced the handle with prompt. So at first sight, going through multi-prompt semantics does not seems to buy us much because the overall process is still the same. However, now we have separated the searching from capturing, and it opens up the way for optimizing each part individually, which we will do with evidence parsing and bubbling. First, we avoid searching using evidence parsing semantics, where instead of searching for a handler in the evaluation context, we will push down the current handlers as an evidence vector. So to illustrate the idea, let's first get a little bit more space between expressions. Evaluation always starts with an empty evidence vector because now we have zero evidence in this vector. But after handler evaluates to prompt, it inserts itself into the evidence vector for the rest of the computation. Now we have an evidence for read. And at this point, the first perform ask can directly take the current evidence vector, look up the evidence for read, which gives us M1H1, and we can directly generate yield M1. So now we don't need to search through the evaluation context because we can directly get the handler marker that we need to yield to from the evidence vector. So this is the essence of evidence parsing. And more importantly, such a lookup can even be implemented efficiently in constant time. So in particular, in a system equipped with effect types, as in the case of Koka, then the effect type will correspond exactly to the runtime shape of the evidence vector. And if we know the effect type at compile time, we can statically determine the index of a handler. Well, we can even do more. As it turns out with evidence parsing, we can even avoid yields by evaluating tail resumptive operations in place. So tail resumptive operations are of this form where the resumption is directly resumed with an expression E. So this is also the syntax you can use to define handlers using a function or value. For example, function, yeah. And for example, f in H1 is of this form. And this is not accidental because, as Dan has already mentioned, almost all common operations used in practice are of this form. They are tail resumptive. And for those operations, once we yield up, we will immediately resume with the result of evaluating E. But that's not necessary because we can directly evaluate E in place. And in this case, since we can already get H1 from the evidence vector, we can replace this yield M1 with the tail resumptive body, in this case 1, and we will do the same for the second perform, so we will be able to evaluate the whole expression without even doing any yields. One subtlety of this optimization is that we will need an underframe to adjust the evidence vector to preserve semantic correctness, but we are going to skip the details, and interested people can read our ICFP'21 paper. However, not all operations are tail resumptive. For example, if f is of this form, where we do 1 plus k1, then we will get back to yield, and yield is still a non-local and expensive operation. So we use bubbling to make yields local by bubbling it up until it meets its corresponding prompt frame. To see the idea of bubbling more clearly, let's make the code stack more obvious. So for example, in the third expression, we will first yield, whose result will be added to perform ask, and the computation is guarded by a prompt. And we can do the same for the resumption. Now it is more obvious that during capturing, we are capturing multiple frames at the same time. With bubbling, we are going to bubble up the continuation in little parts. When we are yielding, we keep the currently built up resumption as an extra argument to yield, starting from the identity function, and we extend it with each frame one at a time, and until we meet the prompt where the resumption is now complete. Now with evidence parsing semantics, we have made perform local, and with bubbling, we have made yields local. Since everything is local, it opens up a way to implement everything in a monad. With monadic translation, our running example will be translated into a monadic expression like this. So the monad we are using is also regular. It is essentially a reader monad for the current evidence vector composed with a control monad. And we can understand the definition of control monad by looking at the definition of monadic binding of MON. If we bind E with G, we will first apply E to the current evidence vector W. And if E results in a pure result, then we can pass the result and the current evidence vector to G. Otherwise, if E performs an operation and thus generates a yield, we will bubble this yield up and add G to the partially built up resumption. So a control monad is essentially either a pure result or it is a yield indicating that we are performing an operation. You can see all ingredients of the translation in this definition. We have evidence passing, multi-prompt delimited control, and bubbling. At this point, we can use regular compilation techniques to compile the algebraic effects to any target platform. As an example, we show how Koka compiles to standard C. So this is the C code generated for this expression, and we highlight some key components. This context is the evidence passing part, which stores the current evidence vector. When perform ask, as in this case the type is statically known, we can do a constant time array access to find the handler. And we also optimize the representation of the control monad, since in practice, most operations are tail resumptive, and we assume most code will not yield. So we always return results, normally assuming pure, and set a flag to indicate yielding. If yielding, we will perform a yield extend, which implements bubbling. As we can see, all ingredients fit well into this final generated C code, and most importantly, if the code does not yield, as in most cases, the computation will take this happy path, where there is no yield and no allocation. We now show that our sequence of refinements preserve the original semantics of polymorphic algebraic effect handlers. So in particular, consider a user-defined expression E, which translates to a monadic expression E prime in our calculus. And if in the original operational semantics of algebraic effects, this expression evaluates to an integer n, then E prime in the monadic calculus evaluates to the same integer n. So this establishes the soundness of our transformations. Another important theorem we would like to show is that the tail resumptive optimization is correct, in the sense that the optimization is semantics preserving. Here we show that if E is a well-typed expression, then E is contextually equivalent to itself. Well, this lemma may seem trivial to you, as the expression is of course contextually equivalent to itself. But the subtle bit here is that this notation, contextually equivalent, in our setting, is defined in a way where the left expression will be evaluated with without tail resumptive optimization, and the right expression will be evaluated with tail resumptive optimization. And we show that they always evaluate to the same result, and so this theorem gives us exactly what we want. So to wrap up, in this part, we discussed the compilation problem with the traditional implementation of algebraic effects. And then we discussed about the algebraic effects in Koka, compared between evidence passing translation and evidence passing semantics, and focusing on evidence passing semantics as an effective way to compare algebraic effects into polymorphic lambda calculus and also gain performance from tail resumptive optimizations. I think I'm right on time. So this is the part about the theory of algebraic effects. For now, we will take a 30 minutes long break.
There we go. So this talk has like 3 parts, really. I'll start explaining Perceus first, garbage-free reference counting that's guided by the compiler, and then explain a bunch of functional but in place algorithms. And then later, Ning will tell us about the linear resource calculus. This was presented at PLDI a few months ago in joint work with Alex Reinking, Ning, Leo Demura, and myself. And And we really wanted to compile to C, actually Leo Demura as well for the lean language, without having a special runtime system, in particular garbage collector. So we wanted to kind of revisit reference counting. And there's always a bunch of problems with reference counting. Everybody knows it's worse than garbage collection. And in particular, concurrency is troublesome. If you want to increment, decrement reference counts and they're shared, you have to use atomic operations. Cycles, of course, are a big problem. Like if you have a cycle, that it won't be collected by normal reference count systems. And the final thing that's maybe less known is like the precision, and that's what we're going to talk about mostly in this talk. The other things, concurrency and cycles, are kind of mitigated by the language. Like Koka has inductive data types, co-inductive data types, and arbitrary ones. But the inductive and co-inductive ones can never form cycles, for example. So the only way to actually make a cycle in Koka is to use explicit reference cells. And it's so rare that we're kind of okay for now. You have to break them by hand. And we talk more about it in the paper. But what we really wanted to look at first is, can we do reference counting on that subset in a good way? If we use a language like Koka or Lean, which is dependently typed, we have a lot of static guarantees to optimize aggressively at runtime, at compile time. So this is what we're going to try, and that's kind of what led to the Perceus work. So precision, that's kind of an interesting thing. I'll give an example of what I really mean with this. So if you see now, like if there's reference counting implementations like in C++ with shared pointers, or in Rust with the RC of T, or Nin with the finally, like how do they implement reference counting? Well, they look at a function like this, like main, where they create a big list, and then we map a function over it, and then we print the resulting list ys. They will do something like this. They say, oh, I have two local variables, and in the end, I'm going to drop them. And also Swift, even though it can do it differently, currently it does something like this. But it's not great because halfway we have two giant lists in memory, both XS and YS, right? Because XS is really dropped too late. And this can lead to a lot of extra memory usage. So in Perceus, we want to do better and use the compiler more. So what we're going to say is we're going to transfer the responsibility for deallocating access to the map function instead. We kind of see statically that that's the last usage. So we're going to say, okay, map needs to deallocate access. It will own it. And similarly for the print, like print will deallocate ys. And at this point, the access will kind of be deallocated while the ys is constructed. And that will also give us the opportunity to update in place, like I showed earlier during this talk. So I think this is a big thing that's been maybe unexplored in the reference counting. Although it's been forever, so there might be work that does something similar. So here we're going to look at the map function here, and we just said, well, access is now owned by the map, and we need to deallocate, and we're going to do that like as we go. So map will do something like this. It will say, okay, when I see a cons node with children x, 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 then I have to duplicate the reference counts, like increment them for x and xx, because I now just copied them. And then I'm going to drop the node xs, the cons node, which will recursively drop its children. And because I've just dumped them, they will stay there. But the cons node itself will be deallocated. And then function calls, you also own them. So a call is actually, you have to dump it first, the f, before you can call it, because later on we use the f again, right, to pass to the map. And then when we get to the nil, we drop the XS node. Actually, there's also a drop to f here, which I forgot to include. So this is code that you could generate, but actually because we do a compiler, we can optimize this. So actually, Perceus does generate something like this, but then we're just going to optimize these dubs and drops a bit by inlining. So this drop, we can inline it, and it will look a bit like this. It will say, well, if access is unique, like if it's 1, then I can drop each of its children recursively, and then I free the node. And if it wasn't 1, well, I just decrement it, right, from 2 to 1, because I can't free it. So this is the if statement. And when I have this, I can kind of push down these dubs in there. So I'm going to push them in. And now we get something really nice. We see here these dubs and these drops, and I can fuse them together because they cancel each other out. That's really nice. So now I get something like this. And this looks a lot better, right? Now we say, well, it is a very cheap check. Like if access is unique, then just free it. You don't have to dub or drop. So we kind of get rid of a lot of these reference count operations, a ton actually in realistic code. So that's really good. And then we have the like slightly slower path in the case that the list access was shared and it's not unique, right? And we can do a little better because now that we're like freeing if it's unique, we can also say, well, maybe we can reuse those things if they happen to be unique. And that's like here, the cons node kind of matches with another cons node to allocate later. So what we're actually doing is we're gonna create reuse tokens. So instead of saying drop access, we say, well, drop, but maybe reuse it and put it in a reuse token. It'll be null if we can't reuse it. And otherwise, it'll be like still pointing to the thing. We don't free it. And then this cons at here means like we're going to allocate, if possible, at the reuse token. If it happens to be not null, then we just use it in place. And the compiler guarantees it's just of the right size and the right kind of memory we need. And if we do that and we insert the dubs for the children, then we can kind of do the same tricks. We can kind of inline the drop reuse. It will look something like this. If it's unique, we drop the children, but we return the address. We don't free it yet. And if it wasn't unique, we just decrement it and we return null because then we can't reuse it. And this is dynamic. And then we push down dubs again and we get fusion. And now we get a very happy path here where if it happens to be unique, we just record the address. Well, it's like a no-op really in the C code. And then this cons node looks like, oh, if it's not null, I'll just update it right in place. And this turns out to work quite nicely, right? So now we get a algorithm that dynamically adapts to either reusing if the list happens to be unique and basically updating this cons node in place, or we get the persistent algorithm. The list is shared still, someone still holds a reference, and then we'll make a copy like on demand while it's shared. It could also be a tail or part of the list that's shared, right? And this works out quite well, and it's all very regular. It's a regular simplifier that runs, right, that can do this kind of optimizations. So that's very cool. Yeah, so functional but in place. So now that we have this reuse, we can kind of start to think about like, hey, can we maybe always have this reuse, right? So here's again the earlier red black tree example I showed from Chris Okazaki. It's a purely functional insertion. It does red black tree rebalancing, and here you see, for example, that the node here like matches with this node, right? So actually, the reuse analysis in Koka is quite predictable. It will try to reuse this node, right? And it turns out that if the original tree is unique, then this one will be able to be reused, and this one will just override it in place. And actually, if you look here, you can maybe show that. Right, if you look here, the actual code here, you see that this node will like match with this node, or this node, or this node, right? And sometimes there's rebalancing going on, like over here, we see there's like balance left. That doesn't look great, but it's actually inlined, this balance left. And here you see it's always like 2 nodes, and then there's 3 nodes, and 2 nodes, and 3, and 2, and there's always one more. But actually, balance left is itself under 1 node. So every node matches with another node. And it means that at runtime, when you go through this, and the tree happens to be unique, every node will be reused on the way back when it's rebalancing, updating each node in place to be rebalanced. So that's when you actually look at the C code, it's crazy. Like it switches pointers around randomly in these nodes to rebalance, but it does exactly the right thing. It's just something you would never write by hand. Well, people do write it by hand, but it's not so fun, right? Here it goes like auto-magically. So we write a purely functional algorithm, but we get this like in-place rebalancing where pointers get switched like on demand, right? And another thing that's happening is here, for example, in the node, we also do reuse specialization. So you see this node already had 3 fields here that are the same over here. So when this node gets reused, it won't update these fields. It just updates this guy over here. So it's just a single assignment. And we actually can see this. I have the C code open here. Here is the insertion. And you can also see it does the tail call, tail recursion modulo const, like the insertion call here. Actually, is a tail call because it's just node and total read and total expressions. So it can build the node and then just jump into the insertion, like in a tail recursion modulo const. You see it here with the tail call. And here's the first check actually for if it is read or not. And then at some point, yeah, here we see. So we say, oh, it's likely that we can reuse it. So we're actually going to reuse the cons node that we earlier had. And here you see it assigns just the left child. And it actually also assigns the red color again. We still have to optimize that. Like it doesn't recognize that this red is the same red as here. But we'll get that in the future. So this assignment one too much. And then it basically says, oh, and now we do a tail call again for the insertion. So that works out really nice. And then like for red black 3 rebalanced insertion, there's no allocation at all except for the leaf node, which is exactly what we want, right? And the spine is rebalanced on demand. And if we happen to use a tree persistently, so there's still another reference to some original tree that we want to save, like say for a scope, then it will only copy the spine that needs to be copied, right? That's shared, and then share the rest again. And that works out it works out really nicely.
One question we got regarding the code is how predictable is the inlining you are describing for balance left?
Right. So currently, it just started. It's not very predictable, right? So you just have to hope that it gets inlined, right? Actually, you can write here inline in Koka, and now it will always inline it no matter what. So that's one way around it. But it turns out it will inline it because it's only used once. That's another one. But it's unpredictable, right? And also knowing that this will be reused in a sense. So yes, here you can see that, but it still depends on whether the original tree that's passed in is unique, right? So I think there's still language design needed where we can, for example, say, look, we expect reuse to happen here. And if it's not, then warn me. In particular, in balance right, you would like to mark the inner nodes here as saying like, I really hope this gets reused somewhere else. And then it would catch it. If it wasn't inlined, it wouldn't. And then you would see that at runtime, right? And we're still working on language design to do that better, to make the whole optimization be more predictable, more like tail recursion, right? And there too, we actually want to be able to mark, say, this function as like we expect it to be tail recursive, because here too, you're kind of relying on tail recursion modulo cons. May not be obvious, right, that it triggers here.
There is a related question. So, how important is having tail recursive modulo cons to express algorithms in FBIP style?
That's a good question. Thank you. I think it's fully orthogonal. One reason is that first Koka will do tail recursion modulo const transformation, but I think the same FBIP will still apply the reuse whether or not you did this as a tail call or not.
But I think for this case, for this particular function, you actually need both to get the best performance.
Right. You get better performance but you want both, right? But I could rewrite this by hand to kind of not to just do an accumulating argument over here, and then the reuse would still happen. Because that's actually what happens internally, right? Like we first transform it with accumulating argument, then we do it. If you wouldn't do it at all, you just use more stack space. But again, the reuse will still happen. It's just node to node. It doesn't matter kind of when the call exactly happens. Okay, I will continue. Otherwise, we can go way over time. I hope that answered the question. Right. So even though I was now a bit negative, saying like, well, you don't always know when it triggers. It is fairly predictable, though. I don't think it's as bad as like, let's hope for the best. You can see when things you can kind of match up the nodes with each other, right? And it will trigger if it's matched and used, right? So that's not too bad. Here's, for example, an in-order tree traversal. And here you see that the bin nodes and the tip nodes will be reused. And at the same time, you see here the recursive calls. And one of them is actually a tail recursion modulo cons in Koka, but one of them is not, right? Because we have two calls. So this will still use stack space for the depth of the tree. And there's actually a cool algorithm we can do here that relies on FBIP and tail recursion modulo cons to kind of can we do the whole thing without using extra stack space or heap space, right? So this traversal is already using no extra heap space if the tree is unique, because the bin nodes will be reused and the tip nodes as well. But we still use more stack space than we might like, right? So this is a known problem, actually. So Nuth had this problem with in-order traversal without using extra stack or heap space. And Morris had a really nice example of this. I always thought it was like the Morris of Nuth-Morris spread, but actually it's another Morris. So that's something to know about. And this is a solution in C of Morris traversal. And this is visiting a tree in order without using any extra heap or stack space. But it's tricky. It searches ahead at some point to the predecessor, then modifies pointers. Then later, when it gets there, it kind of sees the pointer and it knows that we still have to visit right trees. And it basically like simulates the stack in one of the tree spines, right, to revisit in the right way. Very similar to like the garbage collection trick where you can remember where still to go by basically putting the stack in the structure. But the question is, can we do this nicely in a functional style? Well, turns out that's actually possible. So in particular, we can define a special data type, a visitor data type, that matches with the original tree data type. So the done kind of with the tips, and then we still have to visit the right tree, or we still have to visit the left tree. And what's interesting about this visitor is that actually you can derive it from the tree as the derivative of the algebraic tree data type. So this is there's a really cool paper by Conor McBride where he does these kind of things. He derives these visitor data types, the zippers, like as derivatives of the algebraic data type. And it turns out that this visitor is exactly the derivative of this guy, because it's like this is like a product, and then we get like a sum back, like right and left. And this is basically a list of visitors, what we still have to do, like the stack, saving the stack, what we still have to do. And we can go up or down the tree. And now we can define an in-order traversal that takes the initial direction will be down the tree with an empty visitor. And then we look at the direction. While we're going down, like going down a left spine, and we see a bin node. Oh, actually, one thing to note is that all calls are tail recursive, so we don't use stack space. And then one bin node, if you see a bin node, we can have to remember to still visit the right node. So we create a bin R, where we say, oh, still visit this right node, and whatever we were doing up till now, the rest of the visits. And you see that this bin R matches exactly in size with the bin node. And then we keep traversing down the left one until we hit the tip. And then we're done, but now we go up to the tip again. But when we go up, we hit these bin R nodes, like saying, oh, still visit R. So now we make a bin L node to say, okay, we go down the right tree and we apply our function because we're in order. But remember that when we get back, we have to combine the results again. This is the bin L. And now we combine the results finally back to a bin again, where now both L and T are updated results from the visits down, where we applied the function. And now you can see that these bins get reused in place by bin Rs, and the bin Rs by the bin Ls, and the bin Ls by the bins. And now we don't use any stack nor heap when the tree is unique, which is quite amazing. And it's a purely functional algorithm without doing any pointer manipulation or anything, right? And then, of course, at runtime, crazy pointer manipulation here, like how we reuse all these nodes and how they get updated. But nothing to see there, right? So this is, to me, this is like really, really cool. And I'm now working with Anton Lorenzen, a master student, to do more of these. And we've found various other cool places where this applies, especially with respect to zippers, right? I think that we're running out of time. I'll skip a bit through the dark side because I don't want to talk about the problems, of course. But cycles, no cycle collector yet. We want to add a cycle collector, but it brings back a lot of the garbage collection issues. As Ningni will explain soon, Perceus has no garbage at all. Anything is freed the moment it can be freed. So it uses like minimal amount of memory. As soon as you introduce something like a cycle collector, you do lose that, right? So there's something there. I will skip atomics. Actually works out quite well. So I wanted to just highlight some of the benchmarks. There was earlier a question about this too, especially with respect to OCaml. So here you see the red-black tree, and red is Koka all the time, like at 1. And then it's compared on a bunch of benchmarks that do lots of like tree-like manipulations, derivatives, end queens, and constant folding. And this is the red-black tree insertion. And you see here, yellow is OCaml, and Haskell is the teal, the light blue here. And I think it's interesting to see that OCaml is pretty close to the performance of Koka, even though it uses a garbage collector. And Haskell, right, we saw that earlier, it's like 2.5 times slower, and we're very close to Extra C++ here, right? And I think another interesting one is the one here. It says CK, and it means checkpointing. So every 5th tree that's generated, or 10th of the 42 million, is like put in a list. So there's a reference to subtrees that are shared. And the expectation was that the reference counting would do much worse there. It's now much more shared, so we can't always reuse, and we also have to do more reference count operations. But actually, it turns out that it does better at that when there's more sharing, and the garbage collectors have a lot of trouble as well. And I think that might be that there's more copying going on, and that like invisible work that the garbage collector has to do to still maintain those shared trees is also expensive, right? Especially if to revisit live data, while a reference counting implementation never revisits live data, right? It when it deallocates, it does that, especially in Perceus, because it's garbage free. The moment you do your last use of something, you also deallocate. So you have a great locality. And I think that bears out here. And sometimes it gets crazy with like constant folding. I think reuse really, really helps to prevent a lot of garbage to be collected otherwise. Yeah, well, right. Sometimes reuse is really important. We see this here. Sometimes it's not. And there's still more research that needs to be done. All right, that's it. Let's take a few minute break. Like at least 3 minute break, and then Ning Ning will tell us all about the beautiful linear resource calculus that's behind the Perceus reference counting.
So this part is more about the underlying theory in FBIP. Yeah, so we got a calculus which we call lambda1, and it is a linear resource calculus and established the theoretical foundation for FBIP. So first, Dan showed us already like how the compiler turns a program into a program annotated with reference counting instructions. And now we will take a closer look at what is inside this compiler. So inside this compiler, we have Perceus implemented, but Perceus is really just a syntax-directed algorithm of lambda1. And the design of lambda1 is closely based on linear logic, and it has an operational semantics in an explicit heap with reference counting. So in the formalism of lambda1, we start with essentially an untapped lambda calculus extended with explicit binding and pattern match, and it elaborates the expression into expressions with explicit dump and jump annotations. So notably, to catch the essence of precise reference counting, lambda1 does not model multiple references, so we won't get cycles. The elaboration process is captured in this judgment. So in this judgment, we have two contexts which records resources in scope. So delta is the borrowed context and gamma is the owned context. And the judgment transforms E on the left into an expression E prime on the right with explicit reference counting operations. So to illustrate how this elaboration works, let's go through some rules in lambda1. So the key idea of lambda1 is that each resource in the owned context is consumed exactly once. So for example, in the variable rule, we can consume a resource if we own it exactly once. So similarly, in the lambda rule, for ownership passing semantics, we must own all three variables of the lambda and own them exactly once. So we will be able to consume them when we enter into this lambda. Since each resource can be consumed exactly once, a resource needs to be explicitly duplicated, as in the rule dump, if it is needed more than once. And in this rule, we have X either borrowed or owned. So you can dump an X if you borrowed it or if you own it already, and you can dump it so you can own it twice. And after explicit dump, we will increase the occurrence of X in the owned context. So this owned context is essentially a multi-set where you can have occurrence of variables multiple times. And dually, a resource must be explicitly jumped if it is not used, and we will remove it from the owned context. Moreover, the application rule is a little bit tricky because we got two expressions to deal with. So in this rule, we split this owned environment into two separate environments, gamma1 and gamma2, for expression E1 and E2 respectively. And each expression then consumes its corresponding owned environment. And most importantly, since gamma2 is consumed in the E2 derivation, we know that resources in gamma2 are surely alive when deriving E1. And thus we can borrow gamma2 in the E1 derivation. So here, this borrowed context grows when we derive E1. But for both E1 and E2, they will all have this gamma in their borrowed context because that will surely be alive before we enter into this application. And this we will skip the rest of the rules, but I hope this introduction of the variables and the dump, jump, and application will already give you some sense about how this system works. Now we can present Perceus as syntax-directed linear resource rules. So the judgment maintains more invariants that will keep holding during the derivations. First, the borrowed and the owned context will always be disjoint. So if you own a variable, you won't need to borrow it, and if you borrowed it, that means you don't own it. And in particular, Perceus rules are set up to do precise reference counting. So that means we delay a dump operation to come as late as possible, and we generate a jump operation as soon as possible. For example, here we have shown this declarative application rule where we split this owned context in a non-deterministic way. But for Perceus, in this algorithmic version of the application rule, we will find a good split of the environment. So we pass the intersection of gamma with the free variables in E2 to the E2 derivation. So because we know E2 will need those resources to be able to derive to E2 prime, and then we can pass the rest to E1. Also, for lambdas, Perceus detects whether the binding is actually in the free variables of the body. And because if it's not in the free variable, then that means we don't need this variable and we can drop it immediately because it is unused. So this is how Perceus deals with precise reference counting. Is essentially just a syntax-directed derivation of the lambda 1 calculus, and we are more eager with deriving jump and dump because we predict, we detect exactly how each free variable is used, and we insert dump and jump instructions as appropriate. And I encourage the people to read our PODI paper if you are interested to see more formalism. Now we define our target semantics of a reference-counted heap. So sharing of the resources will become explicit. So the judgment says that an expression E under a heap H steps into another expression E prime under a heap H prime. So specifically, we will have 3 sets of operational rules. In the first set of rules for lambdas and constructors, we will allocate the resources in the heap. So if we evaluate a lambda, in this case, we will allocate the resource F in the heap, and then we will return F, and similarly for the constructors. And then the second set of the rules, that's beta reduction for applications, pattern match, and variable binding, where we will insert necessary reference counting instructions. In the case of lambda, for example, because we keep track of the free variables inside a lambda, in this case ys, we can dump ys, and then we will jump, because we just used f, so we will jump f, and we will substitute the variable x with the value z inside E. And the final set of rule reduce reference counting instructions in a more or less standard way with dump increments reference and jump decrements references. And when the reference count is 0, we will free the resource from the heap and also recursively jump its children. Now, with all those definitions, we can prove that Perceus is precise and garbage-free. So to be able to give the definition of precision, we first need the notion of reachability. So we say that a resource X is reachable in terms of a heap H and expression E if X is a free variable of E, or from another reachable resource Y, X is reachable from the resource V bound to Y. So the reachability essentially defines that X is needed for the evaluation of E. Now we can formally prove that Perceus is precise and garbage-free. So the statement of the theorem goes like this. If we have an expression E, like a user-provided expression E, and we elaborate it into an E prime, so E prime is essentially just E with reference counting instructions inserted. And this E prime, according to our heap operational semantics, evaluates to some value X and with the resource heap H, then for every intermediate state that happens during this evaluation, so for every immediate state, we'll have hi and ei, which is not a reference counting operation, because if it is a reference counting operation, then we will first finish this reference counting operation. So if it is not a reference counting operation, then for all resources in the heap, it is reachable from ei. Well, not exactly, because it's actually reachable from ei erased with reference counting operations. So this statement essentially means all the resources in the heap, they are being actively used in the program. And to see why we got this erase as the operations, we can see some examples. So in this first example, we got a heap which has a resource y points to unit, and it has reference count there 1. And then the expression is the lambda applied to job 1 and then unit. Then this expression is not garbage free. Why? Because we jump y too late. Because y is not used in this expression. So what Perceus will generate, for example, is this expression. So because y is not used, we will jump y as soon as possible. So if you apply this theorem to these two examples, you can see in the first example, we will require y to be reachable from the expression erased with drop y. Then that means y will not show up in the expression and it is not reachable. So this will be this is considered not garbage free, and it is not an expression that will be generated by Perceus. But then in the second expression, because it is still a reference counting operation, so we will let it finish the reference counting operation first. So we will drop y, and then we will get an empty heap with a lambda a lambda applied to unit, and this expression would be garbage free because we have no resources in the heap. So some takeaways. So we have introduced the lambda 1, which is a linear resource calculus, and where each resource is consumed exactly once. So this is closely based on linear logic. And then we present Perceus as the syntax-directed algorithmic system of lambda 1, where we insert dumps as late as possible, and we insert jumps as early as possible. So, and then Perceus has a reference counted heap semantics, and with those definitions, we can formally prove that Perceus is precise and garbage free. And there are still many opportunities for future work. For example, we are interested in investigating cycles, and as Dan said before, we probably need a cycle detector if we want to deal with cycles like more automatically. And then also, we believe this linear resource calculus is a beautiful calculus on its own, and it might deserve more investigation, and it might we could probably use it for something else. And also, for now, our calculus has no borrowing, and also borrowing is one active topic we would like to investigate further. Yeah, so that is the theoretical aspects of Perceus, and with this theoretical aspects of Perceus, we established the Perceus algorithm. So it's really nice that the algorithm has a theoretical foundation. Yeah, I'm done with this part. Shall we take a short break, or you can? Okay, we got one question from Edisco. Not sure I understand theorem 4 with the semantics for lambda 1 and the semantics for basic lambda. Can we use this to prove that a translation lambda to lambda 1 inserting of dumps and jumps is semantics preserving? Yes, we have actually proved that in the paper. So in our paper, we got one theorem, which is if we elaborate expression E into E prime, and then because E comes from just a basic lambda calculus, you can actually evaluate E using just operational semantics from lambda calculus. And then this E prime, if you just erase all the reference counted instructions in E prime, then it would just be the same as E. But we also showed like if you just evaluate E prime using the heap semantics, then you will end up with the same result. So the reference counting is really just doing reference counting, but nothing else.
Right. It won't drop anything that's not supposed to be dropped, right?
Right.
Right. I think
you won't get stuck. Yeah.
Right. So I think that's kind of cool, right? So in a way, it's like minimal, and like it won't drop anything that you're still going to use, and it's also maximal in the sense like it drops anything you won't use anymore directly. Right. That's cool.
Yeah, exactly.
All right, let's take a mini break of until 12:30 to the 30-minute mark, and then we'll do advanced effect handler concepts.
Yeah, cool. See everyone in 5 minutes.
Oh, I see. Noah, I see you have the question on tail calls. Here's a bit less good news. Currently, Koka only does tail call optimization for direct tail calls, like inside a single mutually recursive function. And it doesn't do it across mutual tail recursive calls, but it's definitely something we want to do. It's just that we're resource constrained, right? And one thing that will be very hard to do that for example, implementations like Scheme do is all calls are tail calls, right? So it's completely transformed into CPS style. And this is not something I plan to do. I think it's, well, this is controversial, but I think it's enough to guarantee tail calls for direct recursion, or mutual recursion between functions. And yes, so I don't think we're going to guarantee that every call is a tail call, especially if it would entail doing a full CPS transformation. And then I think currently, because we generate code that's close to regular C, um, that works out really well. Like code generators do a good job of that. And then the other nice thing is that actually many mutual tail calls do actually become tail calls in Clang and GCC if you turn on optimization, because the latest compilers in C actually do this. So trade-offs, right? But I think Koka should guarantee at least between multiple tail recursive functions, and we just haven't gotten to it. And the plan is to actually um, get groups of mutual recursive functions and make it into one that gets an explicit data type kind of in which part of the function you are, right? That's a standard defunctionalization technique. Hey, if you're interested, there's a nice project, right?
Yeah, just to stress it a little bit more. So Koka is still currently under heavy development, so it is not perfect in many aspects. So we encourage more contributions from the broader community. If you are interested. I got one question which I'm not sure I fully understand. Since you already use deterministic deallocation and avoid cycles, have you considered extending your types with effective destructors? With effectful destructors, excuse me.
I hope finalizer. No, right. Um, right. We have no plan to run code when something is deallocated, especially because it's yes, it's deterministic, but it depends on sometimes on the runtime, right? It's something unique, I'm going to reuse it, or otherwise I'm not going to yet deallocate it, right? And I feel that finalization is something that needs to be done um, more deterministically, like written by the programmer at the right points, not as part of the like internal memory management. Much like in garbage collected systems, I think finalizers have been a bad idea because we wouldn't know like when it would actually run. And even in Koka, we have this trouble as soon as we would change anything about the allocation algorithms, right? So I think we don't want to go there. For example, with pure Perceus, we guarantee minimal memory usage. So you can say, we know when something gets deallocated. It would still be hard for you to point that out like in the program. And as soon as we do reuse analysis, we actually hang on a little longer to memory. And we can sometimes in the benchmark see that we use a little more memory when we do reuse. And that's because a reused item will not be freed, because later we're going to reuse it. In the meantime, you may allocate to do some expensive call. You allocate a lot. Now you held on to a little bit more memory than you would otherwise do. And if you would attach finalization to such things, I think it gets very, very tricky, right? So with Koka, you write finally. You use the finally function to do finalization, right? Great. So final part, advanced effect handlers. I think it's supposed to be a little bit more free form. So feel free to ask in the Q&A session, and Ning Ning can also promote you to be speaker if you want to discuss things. I think one thing I wanted to remark one more thing backwards about Perseus and linear typing. There was a bit of discussion in the chat. I think one thing to realize that I find interesting is that with FBIP, even though we maybe need more language to control it better, at least you write one function that does both, right? It's like a pure functional version that can handle both persistent trees and in-place mutating trees, for example, because it does it under the hood, right? And it means I've one function I'm writing in one data structure, like a red-black tree that I'm using. But in other languages where you have linear typing or uniqueness typing, or like C++ or Rust, where you have like ownership, where you choose to do in-place updating, then you have the guarantee of in-place update, but now you only have your in-place updating tree. And if you want your persistent tree, you have to write new functions that are purely functional. And I think that kind of like puts you in a position where you have to make such choice like too early. Like only later in your development, you suddenly realize, I'm using this map, say, for scopes in a compiler, and I want to keep the old one, so later it gets restored. But now you for the in-place updating one, you would have to make a full copy. It can be very expensive, or you have to completely switch your data structures. I think there's a real advantage there. Anyway, on to advanced effect handlers. One thing I wanted to talk about is masking, because this comes up often when you get more when you try to compose more handlers together. And here's an example of that. And we call it mask nowadays. There's many other words that have been used in papers, like shift, which I think is not the best word because it reminds people of shift reset. And there's also, I used to use inject because it's more a type level interpretation. But mask is more a runtime implementation, like where you think about signals that you're masking. So the idea is that you could have multiple handlers for something in scope. Like here I have two emit handlers or operations. And one is the outer one, and the other is the inner one. And when I call emit here, I of course will go to the innermost handler. So I will print inner. But when I would use the mask function, then I kind of mask out the innermost handler and immediately go to the next one up there. So I would go to the outer one because I've masked out the inner one. So you get actually outer there. And again, the mask just takes a function with where it's masked. And I think this masking relates really well to the idea of evidence passing, Because what is mask doing? Well, it removes the innermost entry for emit from its evidence vector and exposes the one behind it, right? So you can kind of see that in the type signature. If you mask some particular effect L, then you must be in a context where L is defined, right? And then the action, it seems like L was never there, right? And this is exactly what happens with the evidence passing. Like mask will just take this one out of the evidence, and now it's for action as if it wasn't there. And in this case, it's about duplicate labels. There will be like two emits, and then the innermost one will be masked. So this is actually important for composition of handlers. And here's an example of that, how that could work out in practice. You may have some action that you want to run, but you run it in a special context. And in that context, you want to catch your internal exception. So here I have an exception handler for throw, but I only want to catch my internal ones, like when I call it here myself, like some internal thing. But I want to run the action in a way that its exceptions will not go to my exception handler, right? It's only meant for my internal things. It's only meant for my internal things. So I can use here mask to kind of like hide from the action that I have internally, that I'm internally using some exception handler. And that's why in the action here, you don't see the exception effect, because action cannot see that I'm using here an exception around it, right? And I think right. I think the interesting thing is that if I would leave out mask here, then also the type would change, right? Then it would suddenly be clear that action would have an exception in there, because it would be clear that the action I'm passing in could actually raise exceptions, which would then be handled by this internal handler, right? But because we have the mask here, it'll just be E. I hope this makes sense. So in an interesting use of mask was shown by Bernacchi, Pirog, in Poppel 2018. Handle with care, relational interpretation of algebraic effects and handlers, where they define state in two parts, like one to read the state, peek, and one to update the state, poke. And actually it's two separate effects, right? So the state is kind of like consists of two things. And how they do it? Well, they have like a value effect handler. They say, well, initially, when you call peek, I always return the initial value in it. And then you're going to do action. But you have a control one for poke, where you update the state. So if you want to say, I want to update it with X, well, what you're going to do is you're going to rebind peek to a new value, X, and then you're just going to resume, right? So now any further operations after the resume will have another handler for peek in scope. There will be the updated value, right? So the only thing that set is doing, poke is doing, is installing new peek handlers. And to make the type work out, you have to kind of hide that you could mask inside when you're resuming and do more operations. You could mask the initial peek and then still get the old value, right? So we don't want that to happen. So what we're going to do is we're going to mask peek out over the whole thing. So we're going to mask out this handler, so it's no longer visible, and then use just the innermost handler. And then we get the right type. And without mask, the thing wouldn't type check. You get an infinite type where there could be, because there could be infinitely many like peaks on the stack. This is also why it's a terrible idea to implement state like this, because every update, every poke will lead to one more handler frame on the stack. And because that handler frame would mask out its immediate predecessor, it would be like tons of handler frames that are no longer useful, right? Actually, there might be runtime mechanisms to get around that, where you do stack smashing or something. So this overriding, I see there's some questions that I already Maybe I'll just continue until it's more clear. I think here we're kind of overriding peak, and there's actually a way to do it. Here it works out well to just use mask, but it turns out that in general that doesn't quite work. And I would like to show that because I feel this is not actually, I think, described in many papers at all. Oh, I'm going to skip this slide. So here's overriding. So suppose we want to override the emit effect. So suppose I have some action, and I'm now going to say, well, I may already be myself in an emit, but I'm going to override it for action to always put quotes around it. So this emit here will call its innermost handler. That will be provided by someone else, but action will, all its emits will go here, right? So all its emits will now be quoted. So we're overriding it, and that's great, but the type doesn't look as nice as I want it to. Like action still sees it as an innermost emit, this guy, and one outside of it, like this guy that's provided by someone else, that's called here. And why does the type show it? Well, we don't know, right? Maybe inside action, I use mask to like skip the inner one and get to the outer one, like I showed earlier. So it doesn't really abstract it that I'm overriding it, right? It's more like adding one extra. So there's actually a way in Koka, you can just write the override keyword, and then it will do the right thing. Like it will really hide this outer one from action, and action only sees one, sees only this handler. But how would it work, right? So actually there's another kind of mask. There's actually a family of masks that allow you to do this, because you can't do this just with mask. And there's two reasons for this, why you can't use mask. Like if I use mask right outside of it, it doesn't work, because then this emit here doesn't go to the right one. It will like hide the one we're actually using. And if I use mask right after the handler, it doesn't work either, because then I'm masking out our own emit that I want to apply for action, right? So there's actually a override is a shorthand for another form of mask, which is called mask behind, which does the right thing. And what it does, it doesn't mask initial emits, it only masks the emit behind the initial one. So that means inside action, if you call emit, it will go to the innermost handler. But if you would write here mask emit, it will not only mask the inner one, but also the one behind it, right? And I think there's this is like not there's not much literature on this, but it's very interesting that for overriding, you do need this extra construct, the mask behind. And if you look at it from the perspective of evidence vector, it becomes more clear. Like mask removes the innermost evidence from the vector, so you naturally mask it, right? And mask behind doesn't remove the first one, but the second one that it can find. Actually, did I put in the type? No, that's a shame. So if I put the type of mask behind, you'll have two L's in its final type, because it will remove the second one from the evidence vector. And now you can see there's like a family of those. So internally in Koka compiler, mask takes an extra argument which says, well, which one in like how many deep you want to remove the evidence, because it doesn't have to be the second one. You could imagine the third or fourth or whatever, right? There was a paper, I think, by Sam Lindley and Conor McBride, maybe Daniel, where they discussed a kind of a calculus for masking. It might be that that's able to express this. I'm not 100% sure. Maybe someone in the chat knows. Yeah. Oh, so mask behind is very important for these kind of things. And then you can do the state effect that I showed earlier. You can actually write it a little nicer in Koka, because you can just write with override val, and now we'll actually do the right thing. Except still, it would have many handler frames on the stack, so it's not actually something we can use in practice to implement state. I wanted to show one more slide here that I skipped earlier. This is about the local variables that I showed earlier in my examples in Koka. I think one way to implement this, which I think is very nice, would be to have like a specially generated, like for each, so the compiler will translate this into, for each of these local variables, it will install like a local handler for local state, like a built-in state handler, using, for example, the peek and poke as its semantics, with some initial value. And then inside here, you could use that local state handler to set and get it, like I'm doing here, just as a syntactical sugar, basically. And then the moment you execute action, now you don't want action to be able to access our local state, right? So there will be a mask local around it. So inside of here, you'll have kind of a local state effect, but outside, it's completely hidden. And we can hide it completely with the masks, just like earlier. And then now it's like unobservable local state that we have, just with the regular handler that's just generated on the fly, but it has like regular semantics that we expect over state. And I think this would be a great implementation technique. Unfortunately, it's not what Koka quite does at this moment, but it's something I do plan to do in the future because it's so elegant, right? At the moment, Koka actually uses rank 2 types, just like Haskell's run-st to do this. It's mostly because what do you do if you have a whole bunch of variables, and do you want to know how do you kind of generate the right state handlers for each of one? It's kind of a hassle. So we did it differently for now. Yeah, this is actually the most important parts I wanted to show. One other thing was maybe multiple resumptions, or maybe the audience can if people are still interested, we can discuss something that's on your mind and have a more free-form Q&A. Thank you, everyone, for listening. Hope you enjoyed. Thank you, Ning Ning, for awesome theory.
And thank you for the great tutorial.
And yeah, if anyone wants to join in and help with Koka, please contact us. And hopefully we'll show you many more cool stuff coming. Yay, thank you.
Yeah, thank you. Thank you, guys.